In this video, we solve another example problem using the method of variation of parameters. Now we've got a second order differential equation here, but notice that the coefficient of y double prime is not equal to 1. So to cause the coefficient of y double prime to be equal to 1, I will divide every term by sine squared of 2t. And watch what happens. These guys reduce, and we just end up with a y double prime there. And then these guys reduce, and we just end up with a 4y there. And on the right-hand side, we end up with a cosecant squared of 2t. So after some algebraic manipulation, we see that the differential equation can be written in this form, and the corresponding homogeneous equation has constant coefficients. The function on the right-hand side turns out to be this cosecant squared t, and cosecant squared t is not an exponential function, a polynomial function, or a sine or cosine function, and then it's not a finite product or sum of those. It's 1 over sine squared, but the fact that there's that sine squared in the denominator means that's not the same as having a sine function or a cosine function over there. So we're not going to be able to use the method of undetermined coefficients, and we have to use variation of parameters. So what I would suggest is using variation of parameters. And the first thing we do when we use variation of parameters is we solve the corresponding homogeneous equation. So we've got y double prime plus 4y equals 0. Now the homogeneous equation in this case has constant coefficients. So we're going to let y equal e to the mx. And then we'll take the first and second derivative. Every time we take the derivative, we get another factor of m due to the chain rule. And then we substitute into the differential equation. We're taking the first and second derivative only because the differential equation is second order. And so we get this. Y double prime is m squared times e to the mx. Then we add 4 times y, which was e to the mx. We set that equal to 0. And then you can factor out the e to the mx. And we're saying this times this equals 0, but exponentials are never 0. They're actually never even negative. So we have m squared plus 4 must equal 0. So we substituted into the differential equation and we simplified. And then eventually we got to our characteristic equation. Now we just want to solve the characteristic equation. So we have m squared equals -4. And we can take the square root of both sides. Don't forget the plus or minus on the right. So we'll have m equals plus or minus. Square root of -4 is 2i. And we can think of this as alpha plus or minus beta times I, where alpha is equal to 0 and beta is equal to 2. So we've got complex conjugate solutions, or complex conjugate values of m. So y sub 1 is e to the alpha x times cosine of beta x. Alpha is 0, so that's just e to the 0, which is 1, times cosine of 2x. And y sub 2 looks just like that, but you change from cosine to sine. Okay, and now that you have y sub 1 and y sub 2, you can find the complementary function or the complementary solution. It's a second order equation, so we've got two terms, c1y1 plus c2y2. Now, it doesn't matter which one you call y1 and which one you call y2, as long as you're consistent. Once you've made that choice, and that's going to determine which function is u1 and which function is u2 when we use variation of parameters. Okay, so that's our y sub c. Now we want to go back to the differential equation here. Oh, I did it again. The independent variable was supposed to be t, and I made it into an x. Sorry. So I'm going to change it to x now. So the right-hand side is cosecant squared of 2x, and that was what I got after I divided by that sine squared of 2. It was supposed to be a t, but that's okay. When we divided that sine squared of 2 times our independent variable out, we got to a differential equation that looked like this. And because that right-hand side is cosecant squared, not an exponential polynomial, sine or cosine, or a finite product or sum of those, we know that we have to use variation of parameters. So we, from here, are going to let y sub p equal u1 y1 plus u2 y2, where u1 and u2 are non-constant functions. Then we're going to skip a few steps because this is kind of long. And we're going to say by variation of parameters, the following must be true. u1 prime must be equal to w1 over w, and u2 prime must be equal to w2 over w, where w1, or where w is the Wronskian of y1 and y2, and w1 looks very similar to the Wronskian, but we swap out that first column for a 0 and an f of x. And w2 is very similar as well. We leave the first column alone. We swap out that second column for 0 and f of x. So we're letting y sub c equal this, or we found that y sub c equaled that, and then we said, let's let y sub p equal u1 y1 plus u2 y2, where u1 and u2 are not constants, so that y sub p is linearly independent from both y1 and y2. And then we've got our formulas for u1 prime and u2 prime that we found when we derived them in that first video. So if you don't remember where these came from, you might check out that first video. All we did was we took this expression, we differentiated it twice, we substituted into the differential equation. There were a bunch of cancellations because y1 and y2 are solutions to the differential equation. Eventually we get down to one equation with 2 unknowns in it. If we make an assumption that one expression involving u1 prime and u2 prime is equal to 0, then the equation forces another expression involving u1 prime and u2 prime to be equal to f of x. And u1 prime and u2 prime can be found using Cramer's rule. So that gets us to this point. Okay, so we've got our formulas that came from all of that, and we got to skip some steps. Now we're just going to find u1 prime and u2 prime by evaluating those 3 determinants, and then substituting into these formulas, and then we'll anti-differentiate to get u1 and u2 by themselves. So let's find w now, the Wronskian. Y1 was a cosine of 2x. Y2 is sine of 2x. The derivative of cosine of 2x is negative sine of 2x times the derivative of the inside, which is a 2 by the chain rule. The derivative of sine of 2x is cosine of 2x times the derivative of the inside, which is a 2 by the chain rule. So this is this expression here, just evaluated at those particular functions, y1 and y2. Then we multiply across this diagonal. We multiply across that diagonal and subtract. We're subtracting a negative, so that means we're adding. And then we factor out the 2. And we've got cosine squared plus sine squared, and they have the same angle. That's just equal to 2 times 1, which is 2. So we found our W. And let's find the next W. Let's find W1 next. A W1 comes from replacing that first column in the Wronskian with 0 and f of x. And f of x was cosecant squared of 2x. Y sub 2 was sine of 2x. So we've got 0 minus that product. And we can write this way, that cosecant squared is the same as 1 over sine squared of 2x. I'll write that way so that it'll reduce with one of these, this sine of 2x over here. So this reduces with one of those, and we just end up with a negative 1 over sine of 2x, which is negative cosecant of 2x. That's our W1. Okay, and W2 looks very similar. You just take your Wronskian, and instead of that second column in the Wronskian, you're going to replace it with 0 and f of x again. So we had a y1 cosine of 2x. So we've got this here, and we can write this as cosine of 2x times 1 over sine squared of 2x. And we're subtracting 0. And we could simplify that. Let's see. How does that simplify? 1 over sine of 2x times cosine of 2x over sine of 2x simplifies to cosecant of 2x times cotangent of 2x. You could also leave it like that. That might be a useful form to write it in. If you don't rewrite it this way, but you rewrite it this way, you can use a u substitution to compute the necessary antiderivatives. If you do this, then you actually have a basic rule for this cosecant cotangent product. So we've got our W1, and now we have our W2. And then we want to find our U1 prime and use it to compute our U1. So U1 prime was that W1 over W. In this case, W1 was this negative cosecant of 2x. W was equal to 2. U1 is the antiderivative of U1 prime. So we bring the negative 1/2 down. The antiderivative of negative cosecant is natural log of the absolute value of, or it's actually a negative natural log, so it's going to be a negative times a negative. It's going to make that positive. Natural log of the absolute value of cosecant plus cotangent. And if that was just cosecant of x, this would be a cosecant of x and a cotangent of x, and we just multiply by the negative and add our constant of integration and be done. But we've got a cosecant of 2x here. And so we've got that kx modification of our antiderivative rules. If u equals kx, du would equal k dx. So we have a 1 over k times du equals dx. Or alternatively, you can think of it this way. If I take the derivative of something like this, I'm going to have to multiply by a 2. If I'm taking the antiderivative and trying to undo that, I will have to divide by a 2. And so u1 turns out to be 1/4 of the natural log of the absolute value of cosecant of 2x plus cotangent of 2x. And we will choose that constant to be 0 because we're going to multiply u1 by y1, and we don't need a constant times y1 as part of our y sub p because we've already got a constant times y1 as part of the y sub c. So we found u1 prime, and then we use u1 prime to compute u1. That's the u1, u1 is the antiderivative of u1 prime. We choose the constant of integration to be 0. Okay, and now we're going to find u2 prime. u2 prime is w2 over w. So that is cosecant of 2x times cotangent of 2x, all divided by 2. So u2 is the antiderivative of that. Now the derivative of cosecant of an angle is cosecant of that angle times cotangent of that angle times the derivative of the angle. So the antiderivative of this, or that times -1, the antiderivative of this is a negative cosecant function. So I'll bring my 1/2 down, got the negative there, then we've got a cosecant here. But we've got to modify that rule a little bit because we've got a 2x inside. The antiderivative of this is this, but since I've got a 2x inside, if I were taking the derivative, I'd have to multiply by 2. If I'm taking the antiderivative, I have to divide by 2. Don't forget to add a constant, and we'll choose that constant to be 0. So I have -1/4 cosecant of 2x as my u sub 2. Okay, so I've got u1 and u2. So that's enough to find my y sub p. Y sub p was u1 y1 plus u2 y2. u1 was 1/4 natural log of this absolute value. We're taking all of that and we're multiplying it by y1, and y1 was cosine of 2x. And then we're taking u sub 2, which is this, -1/4 cosecant of 2x, and we're multiplying that by sine of 2x. So we're substituting u1, u2, say into the form of y sub p. So I've got this log times a cosine function. I put these brackets here because I didn't want it to be ambiguous. I didn't want it to look like you're supposed to take the log of this times that. I wanted to make it clear that we're taking all of this and multiplying by cosine of 2x. That often happens. We often have some ambiguity in our notation whenever you have a log. So what we tend to do is we write functions that we intend to multiply logarithms by in front of the logarithm. So I would write this as 1/4 cosine of 2x times the logarithm of the absolute value of cosecant of 2x plus cotangent of 2x. And I'm doing that, and I'm adding this to it, but cosecant of 2x is actually 1 over sine of 2x. So when you multiply those together, you just get a 1. So I have this, this expression here minus 1/4 times 1. So that's my y sub p. And y sub c is equal to c1 cosine of 2x plus c2 sine of 2x. Then I'm adding y sub p to that to get the general solution. And then I've got 1/4 cosine of 2x times natural log of the absolute value of cosecant of 2x plus cotangent of 2x minus 1/4. And that's my general solution. And typically I would also state the interval of existence here, but it is a little bit difficult for me to immediately identify the interval of existence here because I have to think about domain issues with the log of this sum of two trig functions, and both trig functions feature a sine of 2x in the denominator. So this is going to be undefined anytime sine of 2x is equal to 0. And it will also be undefined anytime the sum of these two functions is equal to 0 because you can't take the log of 0. And the absolute value will make any negative numbers fine. But there are a lot of little issues there and that make finding that domain, that interval of existence, a little bit tricky. So I'm not going to worry about it this time. Okay, so let's talk through the method again one more time. So you've got a non-homogeneous differential equation, and this one happens to be a constant coefficient equation with a right-hand side featuring this cosecant squared of 2x. So we can't use the method of undetermined coefficients because that right-hand side does not have the right form, so we'll have to use variation of parameters. So the first thing we do is we find y sub 1 and y sub 2, the solutions to the corresponding homogeneous problem. Since it happens to be a constant coefficient differential equation, we can solve that by letting y equal e to the mx. So we differentiate as many times as necessary, we substitute into the equation, and then we get here, and then we say the only way that this could be 0 is if this equals 0. And so now you've got your characteristic equation. You can solve it for m1 and m2. They happen to be complex conjugates, and so you get y1 and y2 featuring sine and cosine functions. Then y sub c is c1 y1 plus c2 y2. Then you say, okay, I'm trying to find y sub p now. So I look at my differential equation in this form so that there's a coefficient of 1 in front of that y double prime. That makes this function on the right-hand side the f of x that we identified when we were coming up with the formulas below. We'll say, okay, given that differential equation, let's let y sub p equal u1 y1 plus u2 y2, where u1 and u2 aren't constants. That way, y sub p is linearly independent from both y1 and y2. And we said, if we differentiate twice and substitute into the differential equation, and we see that y1 and y2 are solutions, so a bunch of terms zero out, and then we make an assumption about one relation between u1 prime and u2 prime, we set that equal to 0, then the corresponding result is that another relation between u1 and u2 prime is equal to f of x. So we've got two equations and two unknowns. We solve that system of two equations and two unknowns using Cramer's rule, and that gives us these formulas for u1 prime and u2 prime. So now we say, okay, that's what u1 prime and u2 prime must be. Let's find the Wronskian and this w1 and w2. Now, it does not matter which one you call y1 and which one you call y2. You just have to be consistent. So I chose y1 to be cosine of 2x and y2 to be sine of 2x. So we substituted those in here, evaluate the Wronskian, and I get a 2 for my Wronskian. Then we swap out that first column with 0 and f of x and find w1. We swap out that second column with 0 and f of x and we find w2. And then u1 prime is w1 over w. And we simplify that. And if we were trying to find u1, we just take the antiderivative of both sides. We get to be here. Then u2 prime is w2 over w. You simplify that. If you want to get u2 back and you've got u2 prime, you take the antiderivative of the derivative. And you end up here, choose the constants of integration to be 0 in both cases because we're going to multiply u1 and u2 by y1 and y2. Then you say, okay, Then y sub p must be this. So we substitute the u1 that we found and the u2 that we found into the form of y sub p, simplify as much as possible, and then the general solution is y equals y sub c plus y sub p.